recording. There we go. And I will start Zoom to record to the cloud too. So we have another backup here. There we go. All right. So I found that once I start recording, the green frame goes away. That's basically why it went away. It had to do with starting to record. All right. Um, so let's talk about the homework assignment first, which was due, like less than a minute ago. All right, so the homework is here. So I want to show the homework first. And this is the proposed theorem, which is kind of complicated, but it's really not quite as bad as it seems. Okay, so you have to first to negate it, and then once you negate it, then you turn it into a CNF. So do not forget about negating it first. Okay, that's really kind of the important part. All right, so we'll go ahead and do just that in the uh, document that I showed a little bit earlier. There we go. All right. So this first part here is negating phi, and once you negate phi, then this is really just as overall negation to what is given to you as phi. And then on the next row, I converted all the implication to the negation of the left-hand side and then or the right-hand side. So I did both at the same time. So this particular implication was also turned into the negation of the left-hand side or the right-hand side. Yes. Or you do what? I typically do implication first because as the result of implication, you might have more opportunities to apply the Morgan's law. So the getting rid of implication is definitely a one-way street because by converting an implication into the negation of the left-hand side or the right-hand side, it does not quote unquote generate another implication. So I typically go for implication first. But you can do it in any order. Basically you just kind of look at what is applicable at the time. The only part that you may not know which way to go is distribution because there may be more than one ways to distribute, and then one way will make it actually worse, and then the other way will make it better. So the choosing of which distribution to use is kind of the the only big question. But between implication and De Morgan's law, you can do whatever is applicable because you both can only get to a certain point because they cannot generate additional cases. But as a general rule, for myself, I always apply the definition of implication first. So after that, there are no implications left, and then I apply the Morgan's law. So to apply the Morgan's law, I apply the Morgan's law to this negation of this or. That's the first one that I did, which is on the outside. Now, whether you want to do it inside out or outside in, that's also up to you, okay? Because the Morgan's law can only apply to so many times. Every time you apply the Morgan's law, you are distributing, quote unquote, distributing negation to whatever is in the inside. So you really can only apply it so many times, and then you run out of opportunities to apply the Morgan's law. And then this one from here, from this row, to this row is also De Morgan's law. So I basically apply this De Morgan's law to this negation of this and here. So the and is a little bit harder to see because it looks like a multiplication. And then on the other side, I also have this negation applied to this and here, and then we have this negation applied to this and here. So I applied De Morgan's law like 3 times, but not in a nested way. So I think it is still clear as to um, how I went from this row to the next row. And then from this row to the row that is after that, it is also De Morgan's law. This time I applied De Morgan's law because we have a negation of this or over here. And then the other one is this is just dissolving um, the parentheses because you have a parenthesized or that is ored with something else, so the extra parentheses are not needed. Um, and then from here to here is Oh, I think I just said that. It's the Morgan's law applied to this negation to this or over here, and then we have this negation to this and over here, which is also another application of the Morgan's law. Then we get to here. So when we get to here, you have no more ways to apply De Morgan's law. So now you have to apply distribution because it's not in CNF yet. So in this case, the distribution is to apply. I'm distributing. I don't know exactly what the term we're going to use, but basically this P and this term here is distributed over the not Q. So as a result, this expression turns into these two expressions here. Okay, so this is the only part where it is slightly confusing, but does everybody understand what I just did with this step? Yes? Okay, all right. And huh? Say again? Yes. So, okay, let me just kind of quote the distribution law here. So in this case, we have A, B, or C, which can be re-expressed as A or C and B or C. So let me point out, which one is which one. So the not Q, which is standing out on its own, is the C, and then um, this P is the A. This P is this A over here, and this entire term, this entire disjunction is the B. Do you see how the pieces fit? Let me let me put it. Okay, I'll just put it like this. So we apply A is okay. C is the easiest one. This to this. Oh, the simplification. Haha, that is absorption. You don't have to do it, but it's nice to kind of get it as small as possible. This is already correct. Yes. Because I only need you to convert it to CNF and not the simplest CNF. So this is a valid answer already. But because you have to do resolution after this, having too many terms is not advantageous. So I simplify it to this one here. Because the simplification has to do with this term, P or not Q, and this term here, the one absorbs the other one. So it's absorption. Yes. Let me actually go to the CNF one and show you which rule is absorption. Let me see. Okay, so if you go back to the CNF assignment, there's one there's two absorption rules. I only used one of them here. Um, Maybe I did not call it absorption. Mm, There we go. So the one that I used is the second one. In other words, if you have A by itself, which can be its own complicated expression, and then the other one is the same expression A, but then it's ORing with some kind of B, which can also be its own expression. That can be simplified to just A. So to apply that to our example here is to look at this as P or not Q or R. This is just P or not Q. So clearly, this disjunction here has everything in this particular disjunction, and it has an extra component of R. And that's why both of these can be this one, okay? This one is absorbed into this one according to the rule of absorption. The rule of absorption, is simply saying that if you have a general expression A, and then you have another general expression which has A, and then is ORing with some kind of B, I don't even care what B is, then it can be simplified to just A. Yep. All right. Which looks kind of odd, right? Because it's like, how can we get rid of B? Well, there are two ways to look at this. Okay, the mechanical way to look at this, I'm sure you guys are really sick and tired of this already, is the truth table. Yes, I think we need to have a truth fairy in this class, as opposed to the tooth fairy, right? Okay, so you can prove this equivalency by using a truth table, but the other way to look at this is really just intuitively look at this. It's like if A is false, then the whole thing is going to be false anyway. Okay, what if A is true? Well, if A is true, then A or B is also guaranteed to be true. So B really does not serve any purpose here. So that's the more intuitive way to look at the rule of absorption. But you can also kind of mechanically prove it using a truth table. But yes, well, it just eliminate one more term, which makes it a little bit easier to do the resolution. All right. So that concludes the first part of the homework assignment. So if you get to this one, or if you get to this one, which is a little bit simpler, they're both acceptable as the answer to the first part, which is turning into a CNF. And then what you do is you combine it with psi from the previous assignment. You go first, and then you go ahead. Yes. Go ahead. Well, the psi refers to the psi in the previous assignment. Um, So this psi is coming from the CNF assignment itself, because I think the resolution assignment refers to that one. Okay, let me double check. Yeah, so now that we have the CNF from the CNF assignment, so it's referencing the psi from the previous assignment. So now we are basically using this as our phi to to see if our psi implies this particular phi. So the way I'm doing it here, okay, the reason why I have to rederive psi from the previous assignment is because I did not save that file. And I totally forgot about the solution to the CNF assignment. So I had to quickly kind of rederive the whole thing, which is this thing here. And then you have the what I sometimes call the superconjunct CNF, which is really the CNF of combining the psi, which is from the previous assignment, the CNF assignment, and the CNF corresponding to not phi, which is coming from the current assignment that is due today. So now you have a much longer CNF, which is from 1 to 7. I numbered these from 1 to 7 so I can show the steps of resolution. So are we still good up to this point? Why we have a seven-term CNF? It is the conjunction between psi, which is from the CNF assignment itself, and also the not phi, which was turned into a CNF earlier in the same document. Are we good so far? So now we want to see if the whole thing can resolve to false or not. Okay. And I was not done yet because I started to do this at 11:30 and I ran out of time. So I can continue to do this, or you guys can go like, okay, we know how it goes, and you don't need me to talk about it. Or if you prefer, I can also spend some time to work on this to kind of get to the bottom of this. Which way do you want to go? Hmm? Resolve it? Okay. All right. So I have done some parts of it because I can see I can single out P relatively easily. So between 1 and 5, I can single out P. It's always good to single out an individual variable because then you can use it to kind of simplify the other ones too. So I can simplify and get P out of, single out P. I can also easily single out R by combining 6 and 8. So I'm reusing P by itself right away and ask, okay, who has not P? 6 has not P in it, and between 6 and 8, I can simplify to just R. Is that okay? All right. So then I look at both P and R and ask you who has the negation of R. So the negation of R does happen, but it doesn't happen to expression that only has two variables, but I'll still take them, right? So between 3 and 9, I can combine those and become not S or T. Between 7 and 9, which is this one and this one here, I can combine those two to become not Q or S, and then 4, 9 also will work. So between those two, the not R is gone on 4, so it becomes just a Q or T like that. But I have not singled out another variables yet. And then 11 and 12, between 11 and 12, I can get rid of the Q, so it becomes S or T. And then between 13 and 10 and 13, between this one and this one, I can single out t by itself. But singling out t is useless because none of the term has not t in it. So t by itself is like, okay, we can get to t, but we're not going to be able to use it for anything that is productive. So now we have p, r, and t all singled out. So now the objective is to see if we can single out not p, because if that we can do that, that'll be great. Not p is found here, which means we have to single out not R to get to that. But if we can single out not R, that would also resolve to this. So that's kind of circular reasoning, kind a little bit of that. So not R is found here, and we can see if we can single out this not R. But to do this, we also need to single out the not S over here. And there's another single not S here. I don't think we can single out the not S. Sorry? Yep. So that means our hope is the Q. There's a Q here. There's a not Q over here. To single out this not Q, it would not be easy to do it. So we can look at this one, not Q or S. So we can look at not S. Can we single out this not S over here? If I remember correctly, this is not supposed to be a dead end. It should resolve to false. I just cannot see an easy way to get to false right now. Did you guys resolve to false? No? Okay. So it's not, well, yeah. So basically, I just reasoned out by looking at the variables that it cannot resolve to false. Because I look at each one and go like, can I single out this one? And I cannot. Can I single out this one? No, I cannot. So if the whole thing cannot resolve to false, then the conclusion is phi is not a theorem of psi. Okay, that would be the correct, conclusion. The conclusion is not that phi is false. Phi itself may or may not be false depending on the values of the variables. It is simply not implied by psi. Yep. Two wrong turns make a right turn. That would still be incorrect because the assignment is really to test whether you can perform the steps of resolution correctly, and also to kind of work on it using uh, the correct side. Yep. Unresolvable. I see. Yeah. Go ahead. Yep. Mm, can you be more clear about what you said? You're talking about this CNF? Yeah, what about it? This is the current assignment. This is the negation of, this is the CNF corresponding to to the negation of phi. Well, phi and not phi is definitely going to resolve to zero. It did not. Oh, no, no, no. Those two, for sure will resolve to zero, just by looking at the expression. Yeah, but you have to combine not phi and psi, and that you want to see if that can resolve to zero. Yep. Yep. The module, like the notes. You mean the homework? In my notes? Okay, so that's in my notes. Let's take a look. Propositional logic. I mean, that whole module has one single module, has single, so it has to be coming from here. Huh? In this module, right? Okay. Completeness of CNF. Okay. What about that? You mean this? These have nothing to do with the psi and the phi that we are working with. I'm just picking out two Greek symbols to indicate that this implication can be re-expressed as the negation of the left-hand side or the right-hand side. So that has nothing to do with the homework assignment. Okay. Yep. 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 You can do it that way too. Yep. You have to show me how you come to the conclusion. So it has to be a sound argument. So either you do all the possible resolution and you say, okay, from here on, all the additional resolution will only resolve to something that is already listed, which is going to be a long list, but it can be done. Or you can argue like what I just did, that we have to, the only chance to resolve to a zero is to be able to single out the negation of this. But to do that, it becomes a circular reasoning, so there's no you can argue that there's no way to resolve to zero. But that logic, that argument still has to rely on resolution. So it cannot be, just a gut feeling that it won't resolve to zero. Yep. Yes, you could. So the truth table approach is outside of what the question is asking, because the question is asking, can you use resolution to show me the end result of the whole thing? So you can use the truth table approach to prove that you're right, but you cannot use it as the actual answer. You can include it in the answer and go like, okay, this conclusion, because I cannot do further, I cannot resolve the whole thing to zero, is consistent with the truth table that the whole thing is not all the rows are zeros in the super CNF. Yep. Can the computer can you automate the process? of converting to CNF? I would suspect the answer is a yes. I have not done it yet, but I would suspect the answer is a yes. Because it's not because it's not a general Boolean algebra question because we want to get to only a certain state of a CNF. And as I have already kind of demonstrated, especially with a computer, because with a computer, even if you apply the wrong distribution, it will still work because you can basically do a 6 term by 6 term FOIL, which generate like 36 terms, and then the simplification process is very mechanical. So you can still do it that way, even though by hand I would not have done it that way. All right. So are we doing okay so far with this topic, which actually helps to address the exam two because exam two is going to have questions regarding CNF resolution and also propositional logic. Yes. Hmm. Right. Yeah, so you have to show me all the results of all the resolutions, and then you have to make a statement to say that there are no further possible resolution steps or results, and as a result, because we cannot resolve to false, then phi is not implied by psi. Yeah, it has to. You have to explain the conclusion. Why do you come to that conclusion? Yep. Now, in the exam, I will only give you cases with only like up to 3 variables. So 3 variables makes a very big difference compared to 5 variables. Because with 5 variables, the total number of possible disjunctive terms is what, 3 to the power of 5, which is 270 something. Is it? Yeah. Hmm? 243? Okay. So there are 243 possible disjunctions, but not all of them will be in the steps, in resolution. With only three, then you have 3 to the power of 3, which is only what, 27. And once again, not all 27 will be part of the results of resolution. So the expressions involved in resolution is going to be a significantly smaller subset compared to the 27 possible expressions. So in the test, it will be far more doable compared to in the homework assignment where you have a little bit more time. Is that okay? All right. Shall we move on to, can we go back to discrete probability, or do you guys have more questions about exam two, which is next Monday, not this Wednesday, it's next Monday. Yeah, because I made a boo-boo, because I made the announcement somewhere to say that, oh, the exam is going to be on the Monday after next Monday, referring to today as the Monday. Um, and then in class, I forgot that I made the announcement about that. So I go like, okay, we'll just use the later date. So is anyone who thought that the exam was going to be this Wednesday complain that I delay that to next Monday? You don't have to make your complaint here because I know you might get some reaction from your classmates. So you can complain to me after class in private. But it's next. We don't meet on Thursdays. You can try to confuse me, but I still process what you said the same way. So next Monday it is. Okay. So if you need the SPS arrangement, it is next Monday that you need to have that arrangement done. All right. Yes. Say again. Question number 6. I think we did that, but I could be wrong. Oh, okay. All right. So we'll go ahead and go over. Yeah, we kind of ran out of time on number 6. Okay, so number 6 is really similar to your homework assignment, except it is a lot easier. Okay, so what I'll do is I'm going to copy and paste it into the notepad here, or we can just do it side by side. I think we can do it side by side. It's short enough that we can do it that way. All right. All right, so I'm going to conclude this one here. This is question number 6 of exam 2, and I'm just going to hand copy everything. Psi is not Q or R, and P or not R, and P or Q, and then phi is a negation of a CNF. That was intentional, okay? Because I think you guys can appreciate being easy to derive not phi. So not phi is the negation of the negation of this, okay? Oops. And then double negation cancels out, and magically, it is a CNF already. Yay! So now to perform resolution, we have psi and not phi, which is, okay, no, I do cheat a little bit here because I can copy and paste. So in the exam, you'll be using your fine writing instrument, and it would not be easy to copy and paste. Okay, so now we just look at this. Okay, once again, I would strongly advise people to use this approach because it's just a whole lot easier to keep track of what you're doing, with which step is to number each item. Oops, 5, enter. There we go. All right. So we look at this and then we say, okay, can we resolve this to false? Okay. And as usual, we want to kind of single out individual stuff. So we look at this whole thing and say, okay, what can we single out first? I think Q is the one that's the easiest between 3 and 5. So you don't have to use this order. You can always use a much more systematic way to do it. So number 6 is to resolve 3, 5 so that we have Q left. Okay, so now that we have Q by itself, we're looking for not Q, and 1 and 6 can do that. Okay, so 1 and 6 can resolve so that it becomes just R by itself. And now I need possibly not R. Uh, not Q is okay. So let me see. What can we single out now? We can single out P, okay, that's an easy one. So number 8 is to combine 2, 7, and I have P singled out. And once we have P singled out, we can have not R singled out. So between 4, okay, this is step 9. Between 4 and 8, I can single out the not R. And then we can now have step number 7 and 9 to become the contradiction that we need. So there's a general strategy to the whole thing. The general strategy is to see whether we can single out individual variables or negation thereof. Okay, because that's how you can use those to help eliminate terms in the other ones in a kind of much more intuitive way. So that's kind of my approach of doing this. Yep. Nope, the order does not matter. There are multiple ways to get to the false all the way at the bottom, but but this is not the complete answer. This answer will only get partial credit. So to give you to have the complete answer, I have to say because psi and not phi is false, we can conclude that phi is implied by phi. It's the other way. Phi is implied by psi, meaning that phi is a theorem of psi. I mean, you don't have to be wordy like me, but but you still have to give me the reasoning of your conclusion, and the conclusion statement itself has to be correct. Because some people just say, oh, this means phi is true. No, no, phi is not true. Okay, we just know that phi is a theorem of psi. Okay, It says if psi is true, then phi also has to be true. But I didn't tell you anything about whether psi is true or not. So you can only conclude that phi is a theorem of psi. All right. So is that good? This is the last question. Yep, go ahead. Yes. So if whenever you want to apply proof by contradiction, what you do is you negate the very theorem that you want to prove, and then you combine that with things that are given to you to be true, and then you see if that conjunction will eventually be false. So in this context, I always give you, which one is the theorem and which one is known to be true, or you can assume to be true. In general, so are you talking about in general, how do we do proof by contradiction, or are you referring to specifically in this context, how do we identify which one is the theorem and which one is not? So in this case, the question says, given that psi is blah 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 and phi is blah blah blah, use the following area to show that phi is implied by psi. So that's pretty clear which one is used as the what is known to be true and which one is the proposed theorem. The one that is implied is the theorem. Yep. Uh-huh. In a certain sense, this is also deduction, but not in a general propositional logic way. So the answer is no if you are referencing, the 20 something rules in the conventional propositional system. I would not be using that system. Yep. Any other questions? Yep. Um, I do not know yet. Yep. But you're but you still need to know the everything within the scope of the test. So you still need to know how to convert a Boolean expression into CNF, and also how to perform resolution and how to interpret the result of resolution. Yep. All right. Any other questions? Nobody's going to ask me, when I'm going to create a question for next Monday. Just like you guys, do your homework assignment. It'll be sometime, probably, on Sunday. All right. Any other questions related to the exam? Yep. Uh-huh. That's an interesting question. I have not thought about that. Okay, so let's take a look at the two distributions. So one distribution is the one that looks like um, the normal algebra one, and then the other one is the one that is not applicable in normal algebra, but in Boolean algebra it does apply. So the other one is like this. Okay, so if you think about it, um, this one get you closer to what looks like a CNF. This one gets you further away from it. Now, once you have this, you can recombine things back into the original. So I think it is mostly going to be, oops, okay, wrong key. So I think it is mostly the second one that is applicable, not so much the first one. But I would not even bother to do distribution until uh, there are no more cases to apply De Morgan's law, because if you apply distribution too early, you might end up with complicating cases where, oh, okay, now I have to apply De Morgan's law to more things than what I really needed to. So I would apply De Morgan's law. I would convert implication to or, and then apply De Morgan's law as much as possible until it's no longer applicable. Then I would look at distribution. Yep, De Morgan's law. Yeah. Mm-hmm. I'm not. You always apply the negation first. In other words, for the homework assignment, we apply the negation right off the bat. This is phi, which is basically essentially referencing this entire thing. That's phi. That is given to you, and we have to negate the entire thing. That's why you see a negation on the entire thing. So once you have this expression, okay, once you have this expression, I personally like to get rid of all the implications first. And then once I get rid of all the implications, then I would apply De Morgan's law until there are no more opportunities to apply De Morgan's law. And then you apply distribution, because at that point, the only thing you can do is to apply distribution. Yep. Question number 4. Yes. Okay. So that was actually just me, not being paying attention to myself. Um, so I was actually not wrong. The Okay, this one is the negation. This is actually NEG, the negation. So this I was right on in that class. Okay, but my mind was thinking in the opposite way, that because what we are looking for, what C1 is returning is a set of counter examples of um, why R is not um, comparable. So I was actually correct to put the elements that I said into that particular answer. Did I give you guys the key to this exam? The key is correct. Yep. Yep. Mm, C1 is not returning a condition. C1 returns a set. But you're correct that the elements of C1, the elements of the set returned by C1, they have to meet the requirement that is expressed here. So the right-hand side of the if and only if specifies what needs to be true in order for that element to be in um, C1. Well, okay, that's a good question. So you have to look at the expression itself. So of this entire expression, which defines C1, okay, which starts all the way from here and it ends all the way here, where are the quantifiers for E in X and for F in X, right? So so the quantifier does not apply to R. So that means you have to look at every possible way to assign the value to E as long as it is an element of X, and every possible way to assign the value to F as long as it is an element of X. So that means um, the number of cases that you have to evaluate for the rest of it is going to be the cardinality of X squared. So if you are to do it mechanically, that's what you need to do. But most people may not need to do it, mechanically. They can just kind of eyeball, what is in R, and then go like, oh, okay, this one belongs in C1, and this one does not belong to C1. Yep. You first, and then Julian. Yep. Question number five. Question number five is easy, but go ahead. Uh-huh. Mm-hmm. Mm-hmm. All right. Well, okay. So the question is about part three, which is about what C0 is returning. Okay. So let's go ahead and do that. Okay. So let me. This is Q4 of exam two, and we are specifically looking at part three, right? Okay. So to do this mechanically, there are as I said, 9 cases that we have to consider. So we have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1. So I'm going to do it kind of the mechanical way. You don't have to do it the mechanical way in the exam because I think with not so big of a X, we can evaluate this without actually mechanically doing it. All right, so these are the possible candidates as elements in C whatever C0Rx is going to return. So now we want to ask you which one is a member. So now we look at 0, 0. Okay, so let me resize the editor. So it's scroll this up a little bit. There we go. And then fit this right under so we can a little bit more space. All right. So when E is 0 and F is also 0, the question is the if and only if applied? Is you know, is this side true? E and F are the same. So on the left-hand side we have true, and then the other one is EF is in R. 0, 0 is not in R, so that makes the negation of EF in R also true. So that means this is a member of C0. And then we look at 0, 1 and we ask, is that also a member of C0? EF are different, so we know this is a member because because E equals F is false. So if hmm? Okay, yeah. Let me think about this a little bit. E equals F implies. So when E and F are different, then the implication is true, which means EF should be a member. So I think the key may be wrong in that case. Yeah, so I have to think about this a little bit more. So there's a chance that the solution is wrong because when E is 0 and F is 1, E equals to F is false. But if false is on the left-hand side of an implication, the implication is going to be true. So if the right-hand side if and only if is true, then the left-hand side also needs to be true, which means 0, 1 as an element of C0Rx also needs to be true. So I think the solution may be wrong in that case. Because 0, 1, basically anytime you have the two different elements being different, they're automatically members. Yeah. All right. Oh, question number 5. So we move on to number 5. So question number 5 is for you to fill in the truth table. Do you want to do this part or just the other part? Yes, you can do it that way too. But we can evaluate it, just for exactly what it is. Um, so we have the negation of this conjunction implying the right hand side, which is here. Um, well, we can work out the entire truth table. Q5. So we have P, Q, R, psi. So we have false, true, true, true. Okay, so if they're all true, then the conjunction is going to be false. Not false is true. And then we have the right hand side has one negation. So this is going to be false. Is that okay? And then the next one is true, true, false. Okay, so R itself is false. So that means this entire thing is false. The negation of false is true. Uh, there's a not R here. Q is true, so this one ends up to be true. So now we have false, true, false, true. And with this one, Q is false. So if Q is false and the other two are true, then the conjunction is true, not true is false. So the whole result is going to be true. And then the next one is, oops, true, false, false. Okay, so P is the only one that is true. Everything else is false, which means this conjunction itself is going to be false. Not false is true. And then we have to evaluate the right-hand side, which is not R and Q. Not R and Q is going to be false. We have true implies false, which is false. Are we doing okay so far? Do you want me to finish the whole table or no? Okay. Yeah. I cannot listen to myself a little bit too long. But you get the idea, right? You just kind of evaluate each possible case. But to convert it to CNF, I think that's more fun. Okay, so not QRP implies not RQ. That's the entire expression. All right. So let's try to practice what I just said about the process. So you convert the implication to a negation of the left-hand side or the right-hand side. That's usually my first step. So I'm going to do it exactly like that here. So that means I apply negation here and then turn this into an or. Huh? No, this is correct. The overall, this is overall, for this pair of parentheses is not needed. Yeah. So, yep. Go ahead. Does Okay. Could you repeat that question? I'm not sure what you mean by pulling an and out of the. Yeah. So, okay, let's take a look at the De Morgan's laws. There are two of them. The negation of P and Q is not P or not Q. The negation of P or Q is not P and not Q. Yeah. So those are the two De Morgan's laws. All right. So from here, we have, I can remove all the unnecessary parentheses. So we have a conjunction on one side, and we have a conjunction on the other side. So this is one of the, uh, so we are still applying distribution here. We can do a FOIL. So in this case, this would be a 3 by 2 FOIL, which has 6 terms. Do you guys see that? Okay. So now we have, um, Do you want to see it like a linear one, or do you want to see it as a table? Well, as a table. It's kind of a table. Okay. So if you want to see as a table, we have not Q, R, P as our columns, and then we have not R, Q as our rows. So each cell in the table is a or between whatever is at the intersection of the row and the um, column. So this one becomes not Q or not R, and then this one becomes R or not R, and then this one becomes P or not R. And then on the next row, we have Q or not Q, and then this one is uh, PQR, so Q or R. This one is P or Q. Is that okay? So it's a 3 by 2, which a foil, and then all of these terms are now ended together. So now we have not Q or not R, ended with R or not R, ended with P or not R, ended with Q or not Q. Now, if I were to do it by hand, I would have done simplifications, somewhere already. But this is the mechanical way of doing it. So this whole thing, can be simplified to Q, not Q, or not R. R or not R is, this is just true, okay, which is simplified out. Then we have P or not R. Q or not Q is also just simplified out. Then we have Q or R, and then we have P or Q. And that's the answer, I believe. Is that okay? Yep. Say again? I just could not hear you clearly. The way the table works is we are doing a FOIL between, so there are three terms over here, and it is going to be cross product with this one. So the three here are the rows, I mean the columns, and then the two here are the rows. And then each cell in the table is representing one of the result of the FOIL. Yep. Absorption. I don't see how absorption can be applied here. Because in order to apply absorption, you need one disjunction that is completely overlapped with another one. And here we only see intersection, but we don't see quote unquote subset. So absorption cannot be applied to simplify. Okay. Yep. I missed something. Hmm. Okay. So you simplify the whole thing to not R or not QP. Okay. Okay. So let me copy that. Can you repeat what you have? You have not not R or not Q, not Q or not R, and just P. I can do resolution and simplify this side to just P. A P plus P term somewhere. Um, I cannot see how that can happen because P only happens once over here. So once I converted the whole thing to just a or between two conjunctions, P can only be contributed on one side, it is missing on the other side. So P cannot appear by itself. Oh, okay. Yeah, but it's possible that it can this entire side can simplify to just P. That is entirely possible, but it is not by absorption. All right. So by some fluke, you still got to the right answer. That is more simplified. No. Oh. Ah. Okay. Gotcha. Okay. Not a problem. But you can see how I reasoned out why P cannot be a term as a result of the FOIL because the other side does not have a single P to combine the P or P to become just P. So that's why I know the P cannot be by itself. Yep. Um, I do not see any other way to do this without using resolution. So if you use resolution, then we can simplify not even by a whole lot. Because even if you apply resolution, you can only resolve to just P or Q. You cannot get rid of the or Q here. There's nothing to get rid of the or Q. Yes. Say again? hmm Okay, so I can give you an example of the wrong way of using resolution. Okay, so let me ask you this question. If I have P or Q, and then we have not P or not Q, can I resolve this whole thing to false right away? What resolution steps are available in this case? So let's label these. Okay, this is number one, and this is number two. So I can resolve this by using P. Okay, so if I use P as the connection, okay, then I can combine one and two, sorry, and it becomes Q or not Q, oops, Q or not Q, which is the same as true. Okay. If I use the other way to combine 1 and 2 using Q as the connector, then I end up with P or not P, which is also true. So that means I cannot resolve to false. I can resolve, but I cannot resolve to false. I can resolve to true, which is not what we're looking for. But the most common mistake is for someone to look at this 1 and 2 and perform what seems to be two resolutions at the same time and resolve to false right away, and that does not work. Yep. You cannot cancel out one and two because resolution says you can only pick one of the components of the disjunction to perform the resolution. Because the overall rule of resolution looks like this. It says if you have P or not R, and then you have R or less, then this resolves or this implies P or S, right? So you can only use one of the terms of the disjunction to cancel out only that, and then the rest still has to appear in the final form of the result of the implication. So that means, in our case, in this particular example, you can use P, okay? You can use Q, but you cannot use both at the same time. Yep. Yep. It's hard for me to hear you from all the way out there, so I'm gonna come to you. Go ahead. It's a modified form of FOIL. Yes. It is based on just normal distribution, except, you apply that a few times, then it becomes like that. Properties. Yes. Kind of. Yep. All right. Any other questions? Yep. Ilya first, and then Ryan. Oh, possibly. Mm-hmm. Mm-hmm. I see. Yeah, that might be the one that where I only rely on Zoom to record, and then Zoom just kind of terminated itself somewhere in the middle. You can still check out videos from the previous semester. Yep. Okay. Do you have a question about resolution and the what function? The function. So C0, C1. Yeah. I do not know yet. You will still, okay, I can tell you what you need to know. You still need to know how to read quantified expressions, all the Boolean, all the set notations. You still have to retain that information. And then on top of that, you also need to know the properties of relations. So we have reflexive, symmetric, antisymmetric, um, distrib, uh, no, um, transitive, and comparable. So you still have those five. So that's pretty much about relations. And then we have propositional logic, but you don't need to remember all the 20 something Greek names for the ones that people use. There's only so you have to know how to convert a Boolean expression into CNF. You have to know how to perform resolution. You have to know when you are at a dead end of the resolution steps, okay? And what to conclude when you get to the dead end of the resolution steps. All right. Any other questions? Yep. Question number 4. So hopefully I won't be making some mistakes here with the functions, but the general form is still going to be there. Double negation. Yeah, the negation of the negation of ERF. Hmm, you can always cancel it out on your own, right? It's like, oh, double negation cancels out. Except we don't know whether that's double negation because this negation is negating the result of the implication. So it's not double negation. So you have to be able to match the parentheses. Now on the paper, you guys can match your parentheses. So let's just say I give you some crazy parentheses. Huh? No, I do not. Okay. Not that I enjoy arguing with people, but I would like to clarify. Okay, so we have the negation. So I'm just copying this entire part over here. So we have the negate. So we have open paren. The negation of ERF implies FRE. Close paren, close paren, close paren. So you can see. Oops. Okay, keep hitting the wrong key. Okay, so you can see how the first negation is negating the implication. It is not negating not ERF. Yes, go ahead. Why there are two negations? Because that expresses what I want to express. I cannot I cannot tell you exactly why, but because it is what I wanted to express. Because that is no, because that expresses um that the lack, it is not the case that the lack of one way to relate EF implies the other one is not there. Okay, so basically it's saying it is missing both. Yep. then you would have double negation then, but not in the original form. In this form, there's no double negation. Yes, because when you perform the transformation, you're turning the implication into an or, then you are negating whatever is on the left-hand side and then converting the implication to an or. So now you do have a double negation here. So it becomes this, and then you can apply a De Morgan's law on it. So it becomes the negation of ERF and the negation of FRE. And I think by this time you can see how this is saying that if I can find EF like this in the relation R, then it is not comparable because the E and F do not relate to each other in any way. Okay, that was another question earlier. Yep. Yeah, I made a mistake. Ah, hmm? Dollar sign. I forgot to use double backslash because I was okay. So can you defer? Yeah, go ahead. Let me answer your question before you forget because what I am about to say is not important. Um, Let me see if I have a double. So this is not a double negation. It is not the case. So there's nothing wrong with it because I was interpreting my own equation incorrectly because it is still looking for counter examples. So, okay, so I was reading my own document incorrectly because I did not take into consideration this open paren is closed over here. It is not a double negation. So, so I let me correct myself. Okay, let me no, let me correct my own correction to myself. Yes, double negation right there. Um, Because if you consider, okay, let's look at the original expression here and use the R that we are looking at here. What if E equals to 0, F equals to 1? Okay, so in this case, we have the negation of 0R1 implies 1R0, like that, okay? So now we look at, we resolve it one step at a time, okay? So we'll copy and paste this whole thing and get rid of the rest. Okay, so we evaluate this. Is this true or not, given the R that we have here? Okay, so this is true. And what about this one? Well, I mean, what is it? I know it does not matter, but we still want to evaluate. Okay, it is false. Very good. So now we look at what is not true. False. So false implies whatever is true. So now we have this whole thing being uh, 1. So not true is false, which means 0, 1 does not belong in the C0. So, so I was wrong about my own correction earlier. So there was nothing wrong in the question. The answer, the key that I gave you guys is consistent with the C0 that is expressed here. Oof. Okay, yes. Say again. ED, what do you mean ED? On the right hand side? That's supposed to be NEG. So in the exam last semester, I actually told the class to convert the EG to another negation in class during the exam. Huh? It's because I am generating Markdown from inside JavaScript as a string. So I have to use double backslash to escape backslash itself as a string within a quarter string. And I forgot to do double backslash, I did a single backslash. A single backslash n is line feed, which has no meaning in Markdown. And that's why it just ate away the n, and also the backslash is gone. So it just goes like, oh, okay, backslash neg becomes just line feed eg, which is just eg. Negation, neg. So what you see that is highlighted here is just another negation, just like the one on its left-hand side. Okay, would it help if I give you the corrected version of this? Yeah. Would it be helpful if I give you the corrected version of this test so that you don't get confused by this? Okay, give me a second. I can regenerate that. Go over the key. Give me a second. Let me do one thing at a time. All right. So this is exam 2. So it's 1249x2. And I can even give you guys, like the command line that I used to do this is very old school. Nobody's going to do it this way, except for tech, of course. All right. So now we convert it to PDF. And did I give you guys exam 0? Yep. Okay. So let me give you the better version of this. Can I reply to myself in an announcement? Yeah, I can. It doesn't give me an option to edit. Am I missing something? Yeah. Okay, there we go. Can I get rid of this? Yep. And then reattach. All right. We'll see how that goes. Does the key what? -5. Well, the key won't be affected by the correction to the question. So this is, um, yep, okay. So this one shows all the corrections. But then, am I looking at the right thing? Yep. So this is the corrected version. There we go. But I don't know what this is about. hmm Yeah, this one is also corrected. Remember, I said that there's no y. The y needs to be an x. So this is also corrected. This one, I'm not sure. I don't think this one is supposed to be corrected. I think the original is actually correct. I think this one is supposed to be, we are taking out the implication and turn it into an and. Yeah. Yep. That's the thing that's, yep. Yes. So the red one is the one that is deleted, and then whatever is in the same box that is not in red is the correction to it. Yep. Yep. Yeah. No, you were not complaining. You were just commenting on, how the, yeah, go ahead. The left-hand side. Uh-huh. Because most people associate implication in their mind intuitively with, oh, it means if the left hand side is true, then the right hand side also has to be true. So I think it has to do with that mental thing that people have. You're probably like me, where you look at things in a very mechanical way. So you're just looking at these two things and go like, mechanically they're really the same thing. So why do we have two ways to express the same thing? So I can understand your reasoning, but most other people kind of use implication in a more intuitive way of how we use the word if then or implies. So, uh, and then for those people, the implication operator is makes more sense because they don't want to look at it as the negation of one side or the other side. Yep. Yes. Yep. All right. So I'm gonna stop the recorder.